That's okay. I'll do. Again, the colour looks a bit messed up. No, no, no. No, I think it's time to buy a new cable. Okay, so we're having a look at probability trees. Yeah, you can see okay? Do you need to move? Yeah, okay. Can you see my screen from there? Yeah. It's okay. Hang on. I can get the colour back. Come on. Oh. Come on. Come on. No. You have to use your imagination. No. Almost. No. It wins this time. Okay, so probability trees. Yeah. Okay, so last time we were having a look at using tables. And one other way we can represent probabilities is by using trees. So for example, if we have a coin, we can flip the coin and we can get heads or we can get tails. So this is actually an example of a probability tree. And what you do is you write the probabilities of each choice on the arrow. So this is our coin, and we can have heads or tails, 50-50. So this is our first example of a probability tree. Okay, yeah. So of course we can make it more difficult than that. So if we have a die, how many choices or how many paths are there? 6, yeah. 1, 2, 3, 4, 5, 6. And we can get 1, 2, 3, 4, 5, 6. And each probability here is 1 over 6. What you should know is that the total here is 1. And likewise the total here also should make 1. So this is a very simple tree. We should have a look at one that's a little bit more difficult. Okay, can I go down? Yeah. So for example, in this game, there's 2 parts of the game. First, you flip a coin, and then the second part is you roll a die. And you win if you get heads and a 6, for example. Or even make it more interesting, heads and, 6. So for this question, let's draw the probability tree. So we start here. So first we flip the coin, and there's 2 possibilities here. We can get heads, or we can get tails. And this is a 1 over 2, and this here is a 1 over 2. Now, if we get the heads, we then roll the die, and there's 2 possibilities here. We can either get the 6 or not the 6. So we have a 1 in 6 chance of getting the 6, and a 5 in 6 chance of not getting the 6. Likewise, if we get a tails, again, we roll the die, and we can get the 6, or we can not get the 6. So this is a 1 over 6, and then this is a 5 over 6. So this is our first real example. The previous example here, this is too easy for the exam, okay? You're not going to get this in the exam. The exam is going to have at least 2 parts to it, okay? In semester 2, it could be 3, but for the moment we're just looking at 2. Actually, I should give you a bit of vocabulary. So these here, these are called nodes. So nodes is where the graph can separate, okay? And I guess what would you call these at the end here? Here, I'll put some colour back temporarily. There we go. Come back. There we go. Temporary colour. What would you call the green? What name would you give to them? I could call them outcomes. Okay, got that? Time to remove the colour. Okay. Now, there's only one of these outcomes which is actually a win. Which one is that? That is this one here. If you get this, you win the game, but all the other outcomes you lose. So just like in real life, it's more likely that you will lose than win in this game. So I'm making it authentic. Okay, so what we want to calculate now is the probability that you win. Okay, so the way that this works, you look at the outcomes which are win, so that's only this outcome here. And you start at start, and you take the path to win. So we go this way, and then we go across here, and then we go here. This is the only way to get to win. As you move across the path, you have to multiply as you move across. So it'd be 1 over 2 multiply 1 over 6. That equals 1 over 12. Probability that you lose, well, we kind of know what it should be already. What should it be? 1 minus 1 over 12, so that's 11 over 12. To lose, we need to go the same path as before, except down. So that's 1 over 2 times 5 over 6. Or we could go down, and then we could go up on this path. So we add the possible paths together. So it would be plus 1 over 2 times 1 over 6. And then finally, you could lose by going straight down this path. So plus 1 over 2 times 5 over 6. So that would be 5 over 12 plus 1 over 12 plus 5 over 12, which is 11 over 12. But of course, that's what you thought it should be anyways. So the idea here is the probability of an outcome. You have to add up all the paths. And on each path, you need to multiply through. Or multiply along, maybe. So when you move along a path, the probabilities get multiplied. And then when you go to the next path, again you multiply, but you add that answer to the last answer. So this is kind of the key idea about probability trees. Let's have a look at an example which is a little bit more difficult than this. I really want the colour back though. Oh, hang on now. So you think I'm crazy doing this, but it's working. Amazing. Okay, can we go down to the next one? Yep. Okay, so let's have a look at something a little bit more difficult. Well, maybe not too difficult. Actually, just before we do that, yeah, maybe just a little bit of vocabulary. Some people know all their cards in a deck. Deck of cards? Deck of cards. How many cards in a deck? How many do we know? Don't count Joker, by the way. 52, isn't there? There's 52 cards. And there are 4 suits. The first one, hearts. Look, I'll draw it for you and everything. Hearts. What's next? We can go with diamonds. And they're red. So they're the 2 red suits. Diamonds. Okay, what's next? Very good. You obviously play cards. Spades. Spades. And then the last one? No. Yeah, clubs. Clubs. And then within each there are 13 possibilities within each. You have, what's the first one? Ace, 2, 3, etc., etc., until 10. And then after 10, yes? Jack, Queen, King. Okay. I always think everybody knows this, but then there's always one person, you're that person today. There's always one person that says, no, I don't know these. So there you go. There's always one. Hearts, diamonds, spades, and clubs, and then within each there are 13. So, for example, you could have an ace of hearts, or, you could have an ace of diamonds, or whatever. So in total there are 13 plus 13 plus 13 plus 13, which is 52. 52 cards. It's important that you know this for the exam, because in the question they might use words like this: heart, diamond, spade, and club. Okay. Right, let's have a look at an example using this vocabulary. Can I go down? Yeah. So in this game it's a little bit different. The first step is that you flip a coin as normal, like my last game. But the difference here is if you flip a coin and also draw a card, which means take a card. Now, the way this game works is if you get heads, and then if you draw an ace, you win. Otherwise, no ace, and you lose. But if you get a tails, then the rules are a little bit different. If you get a tails, then if you get a royal card, you win. Otherwise, no royal card means you lose. So when you flip the coin, what do you really hope to get, heads or tails? Tails. Well, tails is a little bit better, because then for the next half of the game, which is easier, to get an ace or to get a royal card? And by royal I mean jack, queen, or king. So which is easier to do, to get an ace or to get a royal card? It's easier to get a royal card, because how many of those have you got? Haven't heard the right answer yet? Not 15, not 3, not 16. 12. There's king, queen, and jack for each of the 4. So there's 12 of those. But how many aces are there? 4. So you'd much prefer to get a tails. Okay, let's draw the tree for this. Can I draw that? Yeah. Right, so we start off and we can get heads or we can get tails, and if we get heads, then we can either get the ace or not get the ace, which I'll write like this with a little tick. And then if we get tails, then we can either get the royal card or not get the royal card. Okay, what number goes here? 1/2, and here 1/2. Here is 4/52, and because this must make 1, then this would be 48/52. Here is 12/52. So what's that then? 40/52, isn't it? Okay, I want everybody to calculate the probability of winning on this game. I'll give you a minute. So you win if you get a heads and an ace, or if you get a tails and a royal. Okay, did you get an answer? What did you get? That's it, yeah. 2/13. So it could be 1/2 times 4/52 if you go this option to win. Or the second option is you get tails and then get a royal card. So plus 1/2 times 12/52. This will equal 2/13. Okay, that's okay? Right, let's now look at something more difficult. Can we scroll down? Yeah. Okay, so let's say we buy let's say something like this. So to make this question easier, let's say 90% of TVs are... Where are most TVs made now? Korea or something? Or Japan? Japan? What's the country called for Japan? Is it JP or JAP? Or like JP? PN? APN? JPN, okay. APN. Like, no, that doesn't sound right. So let's just say 90% of TVs are made in Japan, and then we'll say 10% of the other TVs are made in China, which I know is CN, right? CN, isn't it? Yeah. Okay. Now, let's say that 10% of TVs from Japan break. So 10% of the TVs you get from Japan will break. They won't work after 1 year or 2 years, whatever. And then we'll say 90% of TVs from China break. I know these numbers are not realistic. It's probably more than 90%, but we'll go with 90% anyway. Okay, so what I want you to do for me now is you have a TV You don't know where the TV is from, you just have a TV, and you want to know what is the probability that this TV will break. Okay, try and draw the tree, and then tell me your answer. So first draw the tree. You got the tree? Good, yeah. And did you get the probability? Not yet, okay. Okay, so let me draw the tree first. So we have our TV, and either it's from Japan or it could be from China. Now, we know that 90% of TVs are from Japan, so that means 10% are from China. And then it can either continue to work fine, or it can break. Or it can continue to work fine, or it can break. So you know that 90% will continue to work because I said 10% of them will break. And then here I said 90% of them break, so therefore 10% will continue to work. These don't have to be the same numbers. I mean, it could have been 0.8 and 0.2. I just made it the same in my example, but they don't have to be the same. Okay, so probability that the TV will break, that will be 0.9 times 0.1 plus 0.1 times 0.9. So that would be 0.09 plus 0.09, which would be 0.18. So that's 18% probability that the TV will break. Now, the more interesting question I want to give you, and I want you to think about it before I do it, is I want to know what is the probability that the TV came from China if it broke. So I have a broken TV. I want to know what's the probability it came from China. So this here is given. You know it broke. No question about it. You want to know what's the probability it came from China. This is a little bit more difficult, but I want to see if you can do it before I do it. So try it. Any answers? What did you get? No.
9%.
Huh?
9%.
No.
7%.
No. Yes. Good job. Let's have a look at this. gets 1 over 2. So watch what happens. Let's imagine, before I explain the method, let me just give an example with numbers, okay? So let's imagine for a moment we have 100 TVs. How many of them will be from Japan, roughly? Should be 90. And how many from China? 10. Of the 90 from Japan, how many of them should work? Should be 81 of them. And how many of them will not work? 9. And how many here from the 10 from China, 1 of them should work and 9 should not? Now you know that it's broken. So you can only look at these TVs and these TVs. These TVs you're not looking at. So how many TVs are broken? 18. Of those broken TVs, how many came from China? 9 of them, which is the 1 over 2. Okay. Now let me show you how you can calculate that, but I wanted to give you an example with numbers. Okay, why it's 1 over 2. Okay. Right. Can I write here to the side maybe? Yeah. So we will look at this in more detail in semester 2, but for now we can think of this as a problem with a table. Oh, terrible table. So we can either have TVs which come from China or TVs that come from Japan, but it must be from China or Japan. And they can either work or they can either be broken. So if we think about it as percentages, so I said 100 here, but instead of 100, let's say 100%. So 100% of TVs, or 100 TVs, how many will be from China and working? Well, 10 and working, so that's only 1% will be from China and work, only 1%. How many will be from China and not working? 9%, or 9 TVs and 100 TVs. How many will be from Japan and work? 81%, and then 9% there. So what's the total here? Let's make sure the totals are okay. This is 90, isn't it? No. This is 82, and this is 18. The total is 100. And here this is 10, and this is 90, so the total is also 100. So we did this last week. If I said, what is the probability that the TV is from China, given that it broke? Well, that it broke. Well, here are the broken TVs. There are 18% of TVs are broken. And how many of those come from China? 9. So this isn't how we can get 1 over 2. Another way to get the 1 over 2. So let's have a look at another example which is like this, an important example to do with tests. So I just want to give you 2 words. Continue? Or do you need to write this down? Yeah. Oh, no. It'll get too hot. Yes. Okay. Continue? Yep. Right. So I just want to give you 2 words here. So you all understand that when you go to the doctor to have a test, or when you have your car tested, or any type of test, it's not perfect. Okay, so if you go to the doctor and you think you might have some illness, and the doctor does the test and they say that you have the illness, well, there's a chance that you don't have the illness, that the test was wrong. Okay, So the word sensitive is, we'll use an example with the doctor, okay? So you're sick, you have some illness, you think you have some illness, and you go get a test done in the doctor, or pregnancy test, or something like this, okay? So sensitive means the probability that you have the illness, that you have the disease. Sorry, no, the other way around. Sensitivity is the probability that the test is positive. That means the test says you have the disease if you actually have the disease. So what I mean here is you have the disease. The sensitivity is the probability that the test agrees you have the disease. So should this be a big number, a small number? What do you think? What type of value do you think this should be? It won't be 100% because that's a perfect test, which is impossible. So what do you feel like would be a good number for a test? I think 90 plus. Everybody would be happy if the doctor said the test was 99% sensitive. So if you have the disease, there's a 99% chance the test says you have the disease. And specific. So what do you think that is? How specific the test is? What do you think that might be? Well, that's kind of like the opposite. That's the probability that the test says negative, you don't have the disease, if you actually don't have the disease. So what number would you like again for this, for it to be a good test? What do you think? So do you want this to be big or small? Yeah, give me a number would be a good number here. Maybe again 99%. So if you don't have the disease, 99% of the time it will say you don't have the disease. So these seem like good tests. Okay. And then the last thing I'll give you for this question is how many people actually have the disease? So what is the probability of the disease? So we need to imagine some rare disease. Well, maybe not too rare. So I mean, the example here, you go to the doctor. So I mean, I don't know. Let's say something like, we don't want to make too many people sick with this. 1% maybe? Or yeah. We'll say 1% of people have this disease. Yeah. Okay, so first let's draw the probability tree here. So we can start here. So firstly, your person can have the disease or not have the disease. So what's the probability they have the disease? 0.01, and no disease, 0.99. Now, if they have the disease, or if they don't have the disease, it doesn't matter. They think they have the disease, so they go to the doctor in both cases. So if they have the disease, what's the probability that the test will be positive, that they say they have the disease? 0.99. And the test will say negative, 0.01. Now you realize that this situation is quite bad, because what does this mean? This means that the person has the disease, but the test says they don't. But if you look at the probability, that looks quite small, doesn't it? 0.01 times 0.01. So maybe that's not something to worry about, you think. Okay, so here, the test could be positive or the test could be negative. This is 0.99 and this is 0.01. Now this one here, the test is positive when you don't have the disease. Good or bad? Bad, but not as bad as the previous situation, because at least here all that happens is you get more tests. Whereas in this situation there's a risk that you go home and die. So this is quite the one you want to avoid. Okay. So what I want you to do, just like with the last example, you go to the doctor and the doctor says you have a positive test result. So if the doctor says you have a positive test result, this means you think you have the disease. So you would like to calculate, since you are a math student, what is the probability that you actually have the disease, given that the test result was positive. So you went to the doctor and this is what the doctor said. Doc said test results are positive, and you would like to know, okay, so what is the probability that I actually have the disease if my test result was positive? The doctor said it was positive. So it's just like the last example with the TVs. Try and calculate and see what you get. You think you have an answer? No? So my advice again is to make a table. So the way I see the table as going, you can either have the disease or not have the disease, and you can either have a positive test result or a negative test result. So what you might need to do before you can start is calculate the probabilities of this one, this one, this one, and this one. You might want to put those numbers in first. Alright, so we can have a look at it now. So I'm putting in the probabilities. So diseased and positive, so that's 0.0099. Not diseased, but a positive result is 0.000. Oh, sorry, no, I'm looking at the wrong one. Diseased, but a negative result, 0.0001. Not diseased and positive, 0.0099. And not diseased and negative result, 0.9801. So we got a positive result. So we are only looking here. What is the probability that we're actually here? Well, that would be 0.0099 over 0.0099 plus 0.0099. Again, by coincidence, this just happened by accident. It's not always 1 over 2. 1 over 2 here. Now this might be a bit surprising because you would have thought that if the test result is positive, that means you have the disease. But here we just saw that even if the test result is positive, there's only a 50% chance that you actually have the disease. So at the beginning, if I gave you this information, look, If I said there's a 99% chance the test will be positive if you have the disease, and there's a 99% chance that the test will be negative if you don't have the disease, and I tell you the test is positive, you think, oh no, I have the disease. But actually, when you calculate it, it only comes out at 50%. Now the reason it's so small, it's not because the tests are bad. Look here, the tests are actually, these are really good tests. The reason this is coming out as so small is because the disease is not common. It's a very rare disease, 1%. If I was to change this to 10%, let's see how the numbers change. So if I change this to 10%, this would be 10, and this would be 0.9. So what would happen here, 0.10. So this would be 0.099. This would be 0.001. What would this be? This would be 0.9 times 0.01. 0.009, and then this last one, 0.9 times 0.99, 0.891. So which two numbers do I need to add? It was disease positive over both the positives. So diseased, so it's this one over this one plus this one here, isn't it? 0.099 over 0.099 plus 0.009. So now, if I increase it to 10%, anyone want to have a guess at what they think the probability would increase to? It actually jumps up a lot. The probability jumps up to 11 out of 12 chance that you have the disease. It's a big difference, isn't it? So if only 1% of people have the disease, probability that you have the disease if the test is positive is 50%. But if 10% of people have the disease, probability that you have the disease if the test is positive now jumps up to 92%. So it seems very strange to think about it this way, but it does matter how many people have the disease. This number here affects how you can interpret your test results. So the way I see it is, if less than 1% of people have the disease, if the test is positive, that almost means nothing. 50-50 chance that you're sick or not. But as soon as you have more than 10% of people with the disease, if you get a positive test result, probably means you have the disease. Okay. Right, so that's kind of the most difficult example that you could get with probability trees. So I'll let you try these for a few minutes. Again, I need all of these. For the exam, you need to have all of these because we don't have any practice questions from past papers. So if you can do all the questions on page 90, let's try them for 5 or 10 minutes.